So I own one of these Tektronix Model 222 digital oscilloscopes. It's a small, for the period of time this was made, small, handheld, portable, able to be operated from battery power, dual trace oscilloscopes. There was also a 222A and a 224 and maybe some other models in there. The 222 is quite slow. I think it's only maybe 1 megahertz bandwidth, so really, you know, good for audio frequencies and maybe control frequencies in industrial controls and things like that. The kind of signals you would see there. And it works fine, but it didn't come with a battery. And the original batteries in these are lead acid batteries, sealed lead acid, or SLA. If you see that, SLA, that's sealed lead acid batteries. And there's actually 2 of them, and then they're like shrink wrapped together into a block, and that fits into an area that pretty much occupies this space on the scope. And the cover of that is actually the back of this zipper case, which holds the probes when you're, you know, trying to store it, etc. It's got a little bit of the jitters on there. That actually seems to be coming from my signal generator. But anyway, so there's different ways to equip these oscilloscopes in this series with new batteries. There's the nickel metal hydride approach, which works pretty well and it's pretty simple. There are some fancier approaches, one of which I will explore in this video. And there's also the issue of how the batteries, whatever type of batteries you put in there, if your scope didn't come with the original battery packs, it's a semi-proprietary connector from the cable coming from the battery pack where it plugs into the one of the circuit boards on the inside of the oscilloscope. And that connector can be a bit of a trial to come up with these days, and I've done a bit of research and experimentation and found several ways of doing it. There's more, but I found several ways I thought were good ways of doing it, and I will also talk about those aspects of this whole situation in this video. Alright, the design for the lithium-ion battery pack that's going to be mentioned in this video is at this location here, Kitsune-Denshi.net. And when you get there, there will be this message saying there's no content on the home page, and you have to look at the navigation section on the left and go down under projects, and you find the option for the Tektronix 222 battery pack. And when you get there, it has a whole blog on how he decided to come up with it. There's a link to a YouTube video that's an overview of the battery pack. This page needs to be updated, and the guy behind Kitsune-Denshi has emailed me and told me that yes, he recognizes that this is out of date. This NODY Electronics is apparently out of business and is no longer selling the kits, so this link won't take you anywhere useful. He talks about the problem and how there's several solutions. One is to get a different kind of lead acid battery that'll fit into the scope. One is to just have a stack of nickel metal hydride cells, which I also cover in this video. And then you use lithium cells, meaning lithium ion cells, and build a circuit to make them work with the scope. And he decided that even though he doesn't really think that there's that much of an advantage to doing it that way, he decided to anyway. So he goes through the design and considerations why he did things the way he did them. And then he gets down here where he's sharing most of the things you need to do. So there's a link to where you can get various support documents and things. These are the main ICs, the battery charger IC, the boost converter to get from the battery voltage up to what the scope needs to operate, that IC, the comparator IC, and the battery protection IC. Those are the main components. And then you can download the schematic diagram, which, by the way, he has not updated, and it has a number of errors in it. I don't think he really has any plans to fix that. There's a bill of materials which is updated, so you'll find some component values in the bill of material that differ from what's shown for the same component numbers in the schematic. But I don't think there's any errors in the schematic in terms of where lines go. There's also a disparity between the you can get the zip file, which has the Gerber file or Gerber files for the printed circuit board, and on the silk screen there are some test points that are going by one designation, and then the schematic shows them with a different designation in some places, which is confusing. In that case, the schematic is apparently the correct one, and the board artwork is wrong. And then dip trace, you know, the DXF files for the acrylic case, if you want to build an acrylic case. So all those support documents are available there. And then he goes on with the rest of it. So that's where you can get the root support documents on this product. Now, on eBay, at least at the time of making this video, there's a eBay seller called Fix-It Shop that has two items that are available and reasonably priced. And by the way, I should mention that in the Kitsune-Denshi website, the design that's shown is what he calls the revision 1 design, and that's the one that he says, you know, is the best one to build, and that's what his support documents are about. So this guy here is making the printed circuit boards, or having them made based on the Gerber files, and wants $23.27 for one board. Again, there's no components on it, it's just the circuit board. And he's also redesigned the case so it's 3D printable instead of having to be cut from acrylic. And it's a pretty good case design. And that's the one that's shown in this video. So for $19.26 you can get that, and it'll work with the Model 222 or 224 versions of the oscilloscope, and you can choose when you buy it. Well, right now he just says green, so I think he also has black available. These files are not downloadable to the best of my knowledge. He's just designed his own 3D printable case, and you can buy them from him here. And I presume he'll continue to make them available, I'm not sure. Anyway, so that is where I got my printed circuit board and case for this particular battery pack. When that set of parts was received from the eBay seller, it had this piece of paper in here, and it directs it to this DigiKey URL where he has created a complete parts list for everything except the actual lithium-ion cells. So all the parts that actually solder onto the circuit board are in this DigiKey bill of materials. So you can just go there, type that in, and when you're looking at this letter here is a letter O, not a 0. That's important. You won't get the list. So you do that and it'll pull up a list. I think you have to have a DigiKey account and already be logged in before this will work. At least that was my experience. And then you can just go and click one thing and order the whole list of parts. And the price isn't really very high. There's quite a few parts, but they're all dirt cheap, so it's not a big investment. And you'll get, you know, all the parts individually bagged and identified with the component designations that are on the schematic and the circuit board. That's a huge help. And the correct component values when there's disparities between the schematic and the Kitsune-Denshi bill of materials. The correct values are in this list. And I verified that with the guy behind Kitsune-Denshi. So that's nice. So you still have to go out and buy the lithium-ion cells, and you still need to come up with the cable to go between the battery pack when you finish it and the connector on the scope. And I'm also covering that in this video. And then, of course, he links it back to the original Kitsune-Denshi website. So all those things add up. Alright, this is the circuit board. This is the front side. The side where the batteries will clip onto. There's just a little bit of circuitry over here. And then the place where the incoming wires come in and the main fuse. And then flipping it over, we have the side which has more components on it. This is really double-sided here, so the components in this area go along with the components in this area. The parts are mounted on both sides of the board. Over in this area, those are the areas for the cell protection. 1 per cell, 3 cells. And these are mostly left open. They have to do with temperature sensing of each cell. The thermal protection is not implemented in my build, nor recommended by the designer of the circuit, even though there are provisions for it on the circuit board. So I have my new microscope for soldering up circuit boards. And here's the Amazon listing for that scope. The Andonstar AD249 or 249S-M Plus 10.1 inch HDMI soldering digital microscope for electronics repair, 2000x3 lens, 2162p, that's pixels I guess, UHD video, record, soldering, microscope station with helping hands, slides, 32 gigabyte card is included. It's just under $200. So yeah, it's the larger of the two models. They have the same basic thing with a smaller monitor for, you know, 40 some odd dollars less. It's actually a pretty good product. It's pretty easy to use. I thought it worked really well. Although I just bought it for this one project. I used it quite a bit during the assembly of the circuit board. But it's a pretty complete microscope. It has a dual gooseneck LED lighting system, which is brightness controllable. It has an optional tool holder. You could put rolls of solder, various other tools on it, or you can leave that off. It has a anti-static, anti-skid rubber mat. It has a dual gooseneck helping hands padded alligator clip thing for holding objects that you might be working on. That's also optional. You can assemble it or not and take it on or off as you might choose. It has an optional plastic assembly which surrounds the base and has all sorts of little cubby holes and trapdoor covered bays for putting small parts and things in. It has 3 different lenses. One of them that's optimized for looking at microscope slides, of which several examples are included, and there's a separate LED illuminated base if you're looking at microscope slides. That's the traditional glass slides. So all that good stuff, and it'll take still photos and videos, and I think it's a pretty good product. And I'm mostly concerned about these really tiny little pads. Let's see if I can... Yeah, right below where it says R8 and R9. There's actually 2 pads for each of those. They're not even grain of rice size. So pretty small stuff. But if I put them on the scope, they're a lot easier to see, and I can increase the magnification on this, so I can that's plenty big enough to see, I think. I've got the rubber mat on there. The board doesn't tend to slide around on it very much, which is good. If I need to, I'll tape it down, but I'll try to work with it that way. I have my SMD tweezers. I've got all my parts. I'll start with the resistors. They tend to be the smallest parts for the most part. I'm not going to show every step on here. I'll put on all the resistors or something, then I'll shoot a little bit of video. Alright, there's the first resistor. I can't even get a decent picture of it with this camera. But that is, you know, bigger than a grain of sand, smaller than a grain of rice size. Definitely tiny. That should be 330 ohms. And I'm actually going to test it. Yes, that measured out as 330 ohms. I said 390 before maybe, but 330. So the trick here is to put a little bit of surface mount flux on that pad, or that pair of pads. Put just the tiniest amount of solder on one of the pads, use the tweezer to move this in place, sweat that one joint, and then add solder to the other side. That process. Alright, I've got flux over both of these. You can kind of see it there. I put a little solder on that pad. Just even any jitter in my hands and the soldering iron just goes way off the pad. This will be tricky. Well, it's on there. It ain't pretty, but it's on there. Looks like I have a sloppy but electrically conductive blob of solder there. Even with my hand bracing on there, there's enough movement to just have the soldering iron just whipping all over the place there. Very hard to do this when the parts are that tiny. I think there's still enough flux on there to do that one. Alright, that one went on a little better. At least it's straighter. It's a little bit too much in that direction, but I think it'll be fine. Well, I've got the circuit board nearly done. I've got all but 2 of the surface mount parts soldered on, and the reason there's still 2 is because I lost 2 of them. These little smaller than a grain of rice parts, once you drop them, you're not finding them again unless you're having an exceptionally lucky day. And I didn't order any spares, so I placed another order with DigiKey for a couple each of the 2 parts that are missing at this point. But I put all the others on. There's the fuse, and I'm pleased to see that the part that's identified as a fuse in the bill material is actually a fuse holder, and then one of those little micro fuses, the kind that can be surface mounted itself, but in this case you can pull it out and replace it with another one without any soldering or desoldering. And it even tells you which model of fuse is required. There's the connector for the cable going to the battery, or the battery connector on the scope. This is some of the components associated with the battery charger and the step-up converter, the booster, and also the 3 status LEDs. Those are the white rectangles there. So these are the tall components, because this board will sit down in the bottom of its case, and so all the components there need to be pretty flat. So this is the back side. Obviously the battery holder is not soldered on yet. These 3 circuits here, you can see the little surface mount capacitors and resistors there, and the safety, the battery safety IC with its 5 pins, and then the double MOSFET package, which looks like an IC with its 8 pins, and then the R14, which is not populated, is for testing only. Then, so that handles 1 cell, a duplicate circuit for the next cell, and a duplicate circuit for the next cell. With the exception of 1 resistor in those 3 places, none of the components associated with the battery temperature sensors are populated. So these components here are the components associated with the battery charger, which is common to all 3 cells, and its associated larger components are over here on the back side. And then this down here is the booster circuit that takes the lower voltage of the batteries and boosts it to the voltage necessary for the scope to recognize this as a legitimate battery pack. And once again, its corresponding bigger components are over on this side of the circuit board. And those 2 electrolytic capacitors in their cans, it's one of those for each of these 2 circuits. There are 2 ICs in this circuit, and 1 IC in this circuit, a couple of MOSFETs, a power MOSFET and a smaller one, and that's just a diode there, a Schottky diode. The other Schottky diodes for this circuit here are over on the back side of the circuit board. Both of the inductors, because these are both switching type power conversion circuits, so there's one inductor and there's the other inductor. So again, I've got these 2 parts right in the middle of the picture, which are going to be out of focus, that I will put on there once I get them in. I definitely found this new digital microscope I bought to be indispensable for doing this assembly work. I'm going to go over this with my jeweler's loupe and look for cold solder joints. Alright, with the exception of the battery holder, all the components have been soldered on here now. I just did a jeweler's loupe inspection and an inspection through the microscope itself. The jeweler's loupe allows me to look at different angles more readily without having to refocus in the same way. It's just a little more intuitive and quicker, but sometimes the microscope does a better job. I've removed a couple little tiny solder blobs that resulted. I resoldered a couple of, or reflowed a couple of joints that look like they could have been done a little better. So those two electrolytic capacitors really stick up there, but still plenty of room in the housing, I think. Now the lead spacing on these didn't match the circuit board, which is why they're standing up from the board a little bit. I don't know how that happened, but I don't think it'll be an issue. Well, I was going to use the microscope's own recording facility, but I decided to just look at the screen with my camera. Rejigger the lights a little bit here. Those foils there are some tiny foils. That green resistor is one of the ones that's like a 0.1 ohm. Or is it 0.01 ohms? I forget now. And then there's the other one somewhere around here. Yeah, that's the one that's 0.02 ohms. It's the other inductor. That's the first inductor. The 3 LEDs. And their associated resistors. And the fuse holder. And the connector. There's one of the battery protection circuits. You can still see some of the flux that I didn't completely get off there. Shouldn't be a problem. And then it's a little bit out of focus. Again, some residual flux I didn't get off. There's because I went over this with a Q-tip with alcohol, there's still a little bit of cotton fibers. There we go. And then we go over here and have this is a power MOSFET there. I also did continuity checks on any solder joint that looked less than optimal. I would use my continuity tester from the top of the component and then find some other place where the circuit board trace went from there and made sure there was continuity through the solder joint. Yep. This microscope was indispensable for building this board. The ability to see what I'm doing, and this is only 1.9 times magnification. Most of the time I was working at 3 times magnification, except for the larger components like the LEDs and the inductors, then I went down to 2 times magnification. Now obviously that's not the only magnification, that's the digital magnification. This screen has a 0 to 3 magnification in single decimal point increments, so 0, 0.1, 0.2, all the way up to 1.9, 2.0, and then up to 3.0. That's in addition to the optical magnification, which is much, much higher, of course. Now the specified magnification on this, which is in the thousands, is actually taking the actual size of the thing you're looking at, the object, and comparing it to how big it looks on the screen. So if you find something on here which is the size of a hair, and up here it looks like it's 1 inch wide, then you could take that 1 inch and divide it by magnification of 2000 or whatever, and then get the actual dimension of the thing you're looking at. But this scope is certainly a good choice for this application. Cost me a couple $100, but it seems to be well built and it works very well. The other tools I used was a straight SMD tweezers, very fine point. Nice and clean manufacture, no rough edges, no burrs. And then one with wider paddles for grabbing things like the inductors, and then a curved version of the first one. Whichever angle I needed to come in at is what I use those for, but you got to be careful with those. If you let off on them a little bit or squeeze them a little too hard, those grain of sand parts just go shooting off and you'll never find them again. You have to either have ordered some spares or make another order for replacements. And there's the battery holder soldered on. The other thing I want to mention about that, when you're going out to buy the lithium-ion cells for this lithium-ion battery pack, there's a couple different kinds of cells by the same part number, or the type number. That's the 18650. That's what the Kitsune-Denshi battery pack design is intended to use. The 18650, 3.7 volt, 12.6 watt hour, or 3400 milliampere hour lithium ion cell. Now I went with this brand initially, Nightcore, because it looked like it had good reviews for being very good quality and reliability, and these are fairly expensive actually, but these won't work. So be aware that there's a couple of different kinds of 18650 out there. There are ones with the so-called button on the end, like that, just like a normal AA or AAA cell, for example, which are smaller than these. And then there's the ones that are the flat tops, I think they're called, where both ends of it are like the negative end, just a flat plate. The kind with the flat top on it is the kind that you must use with that lithium-ion battery pack design. This kind with the button will not fit. It's longer. Same diameter, but it's longer. Also, the Kitsune-Denshi design includes the individual battery protection circuit on the circuit board, And this battery already has the protection circuit built into it, which is probably why it's longer. There's a little round circuit board in there with essentially the same components on it as what's in the Kitsune-Denshi kit. So don't waste your money buying the kind with the button and or any of them that have the internal protection circuit. You just want the plain vanilla 18650 design. Alright, there's the first test. I have the battery pack plugged into the scope, and it's indicating the green LED, which should mean battery fully charged, which means that if I disconnect the AC power, it should run. Alright, there's the circuit board tucked into its 3D printed case. The one end goes under that ridge that locks that side down. Then this side swings down from top to bottom. We'll put in the cells, and okay, there's what the cover put on the case and screwed down 4 corners. I'll see if this fits into the scope. And there's the green light. Now I'm having some trouble with this. There's something intermittent on here, where sometimes it will semi-permanently disable the booster circuit. It seems to be something flaky with the op-amp comparator circuit, but I haven't been able to nail it down yet. But I have seen it work, so it's almost 100% working. I just need to do a little more troubleshooting. I decided not to delay this video while I did that, because it wouldn't really be instructive. Alright, that battery does fit in there. The cover goes on and locks on properly. So far so good. Yep, it's a working 222, but that's not what the video is really about. Currently just powering it off of AC. Alright, the original schematic is pretty well drawn, but again it has errors in it, and because of the software used to create it, it has some designations kind of crashing into schematic symbols and things like that. So for my own circuit study, as I usually do, I redrew the whole thing and fixed the issues that I had with how it was drawn. So I'm going to use this to go over a brief theory of operation for anybody who's interested. I don't see any other videos out there on YouTube that are covering this information. So let's take a look at the block diagram. So you've got the connector to the oscilloscope here. It's depicted here without the fuse, which is actually in the circuit, and with only 2 pins when the actual connector has 3. And that is a typical Tektronix thing. So if you plug in the batteries backwards, it still works. But I'm only showing the functional pins here. So 1 pin for ground, that's the minus side of the scope connection, and the plus side is the active side. This is where charging current comes from to charge the battery, and it's where battery current goes out to power the scope, depending on what mode this circuit is in. So this line up here is called VCC, and the first thing it does is it goes down to this, it looks like an op-amp, but it's actually a comparator with hysteresis, and it's got an internal voltage reference of 0.4 volts. So it's always going to be changing its output high or low depending on whether VCC is above or below 0.4 volts. In actuality, there's a voltage divider here, which I didn't show or isn't shown in this block diagram, but it's taking VCC and using a voltage divider to divide it down so that its voltage is similar to 0.4 volts. Anyway, so if the scope is powered by AC, this VCC is like 9.5 volts. That'll push the voltage here to the point where it's higher than the 0.4 volts. Remember, there's a voltage divider here. When that's higher, then this signal goes high, and the battery charger part of the circuit is enabled when this is high. There's also an enable for the boost converter, which takes the battery voltage and raises it up to somewhere above between 8 and 9 volts. And only one of these is allowed to operate at a time. They both have an enable, but the enable for this circuit is inverted from this. So when this is high, saying, you know, we've got plenty of voltage here, then it says, okay, go ahead and charge the battery using that voltage or the current coming from the scope, because it's obviously being powered by AC, otherwise it wouldn't be 9.5 volts up here. At the same time, we want to turn off the boost converter because the scope can't use battery power when it's AC powered at the moment. So we invert that high signal to a low, and that disables the boost converter. The battery charger produces the appropriate voltage and current to charge the set of 3 lithium-ion cells, which are just all connected in parallel and to ground, so they get charged. And it pretty much just sits there doing that until such a point where you don't have AC power out here connected to the scope, and it stops producing the 9.5 volt voltage on this signal here. So it drops below the 0.4 volt here at the comparator. That means that the output here goes low. That disables the battery charger because there is no longer sufficient voltage to charge the battery, and the scope is indicating that it's no longer running off of AC. That low signal here gets inverted to a high, which enables the regulator and boost converter circuit. It takes the 3.7 volts or whatever's on the parallel set of lithium-ion cells and boosts it up to the appropriate voltage that the scope expects to see from a fully charged set of its original batteries. And that goes through this diode and out and powers the scope. That's essentially how the circuit works. There's one IC that does the battery charger, one IC for the comparator, one IC for the regulator, that's the voltage regulator and boost converter, and then each cell has an IC to monitor its charging and discharging and disconnect it electronically if it shows an anomaly that puts it in an unsafe situation. Is it being overcharged? Is it being not undercharged but over discharged? Or is there some anomaly in the battery where maybe it's overheating, or it's going to be damaged by being charged or discharged. So there is, again, electronic switches in here, and I'll go over that in more detail here in a moment. So here's the actual 3-pin connector going to and from the scope. The outer 2 pins are connected together. That's the plus side. The middle one is ground. That way, if you flip the connector around the other way, the circuit doesn't change. And that's something that Tektronix has done for a long time with oscilloscopes of theirs that had battery power. There is a 1 amp fuse. And at this point, we can charge the battery with current coming from the scope and going that way, or we can power the scope with current coming out of the voltage booster circuit that's coming around this way and going out to the scope. So let's say we have the 9.5 volts, which is what the scope outputs when it's being AC powered. And is I don't know if it actually has to be turned on or not, but certainly when it's AC powered. So you have the current at 9.5 volts going up here. It's just a power rail. When it gets over in the area of this op amp, or this comparator IC, it has a local decoupling capacitor. Then there's a 1 meg resistor and a thing that's called a resistor. It's called R18, but it's really a 0 ohm shunt. And so it's just really tying these together. And then you've got a 47K resistor going to ground. That's your voltage divider. So that knocks it down to somewhere near 0.4 volts. And there's also a filter capacitor across the lower part of this to stabilize it a little bit. Because 2 inputs here are tied to the internal 0.4 volt reference, and because the other 2 inputs are tied together with this jumper, these two operate the same way, except the voltage divider input goes to the minus on this one, and this one goes to the plus. So these two both switch at the same voltage, but one is going high while the other one is going low, and vice versa. And this IC is actually powered off of the VCC. And it's very forgiving. It doesn't really care whether this is 9.5 volts or whatever. By the time it's divided down here, that's where the action is, but the IC itself can have its VCC be a little bit higher or a little bit lower, depending on what's happening up on VCC. These outputs are open collector, so they can only pull the outputs down towards ground. They can't produce current. So we have to treat all these as if they need a pull-up. This one here goes through this pull-up to VCC, and that's the green LED with an appropriate current limiting resistor. So when this is low, well, I should say, when it should be in charging mode, this comparator is analogous to this one here in the block diagram. So this will be high when it's time to charge the battery. Because these are complementary, this one will be low. When it's low, it's going to give you an indication that the battery is fully charged. Remember that this point here will be on when it's 9.5 volts up here, which means the scope is AC powered. And that means that the battery should be getting charged from the scope power. This will be low when the voltage up here has dropped below a point where the scope would have it if it was being AC powered. So what this really is indicating is, should we be charging the battery or should we be discharging the battery? And this will be the complement of it. So when this is high, that means charge. This one will be low, and that turns this on. So I wrote charging or charged on here, and that isn't really correct. That was just my initial assumption. What it really is it's a power on LED. Just saying that the scope is in AC powered mode and that it's able to charge the battery. So I wrote charged up here, and we really need to think about this more like it's just the power LED. And indeed, the 3D printed case that I bought uses the symbol over this LED, so when this is illuminated, it illuminates the symbol of a power switch, the universal symbol for that. So again, that needs to be thought of as the scope is on and being AC powered. That's what that means. Okay, so let's say that it's calling for charge. So this will be high. That gets inverted by this MOSFET, so this becomes a low, and that pulls this input of this IC, which is the voltage regulator and boost converter, and that disables this, so it won't be trying to power the scope when the scope is actually powering this. This IC here this is sort of an all-in-one battery charger for things like lithium-ion cells. It gets its V in from the VCC. It doesn't care so much exactly what the voltage is. And it has a stabilizing capacitor, a decoupling capacitor to ground. And then the circuit or the IC ground is connected to ground. There are a number of protection features in this IC which are disabled because they're not needed and or because they're being done by something else in the circuit. The first one is current limit protection. By tying that to VCC, it disables that function in this IC. That's being handled by other things in the circuit. And there's also a precision threshold shutdown, which is disabled by the way it's wired up. There's also a timer function, which is disabled by being tied to ground. There's this pin, RNG/SS, which does two things at once. The resistor that's connected from here to ground programs the maximum charge current that it will use on the connected batteries. And this capacitor here causes it to do a soft start whenever you power it on, that it doesn't slam the connected batteries or connected cells with the full charging current. So that's two functions that are there. There's also provision for thermistors, or I think just thermistors, that you can connect up to the battery being charged, so if it overheats, then it will turn off the charging. That is not being used in this circuit. Again, the cells have their own battery charge-discharge protection elsewhere in this circuit. The rest of it looks like a classic circuit of this sort here, where you have a DC power source and a switch which opens and closes at a high frequency. When it's closed, the DC power goes through the inductor and into the load resistance, which is the batteries in this case. And there's also a capacitor there across the load. And then the switch opens up. And there's a couple ways to look at that. One is that when you have an energized inductor, then you de-energize it. It develops a higher voltage of the opposite polarity. So if you think about this as being like a battery, where it's powered from plus over here, then this is the plus side, and this is the minus side through the resistor back to ground. But when it flips, then the plus side is over here and the minus side is over here. So now this acts like the battery, and it continues to supply current, which will come back around through this diode, and this becomes the circuit when this is open. So you're storing energy in the inductor, and then you're utilizing that energy when this switch is opened up to continue powering out here. And because the voltage on this is higher when this is open, at least briefly, the average voltage developed across this is higher than the DC voltage here. But a lot depends on how frequently this switch is open and closed. If it's only operating slowly, then this voltage will be lower on an average. And if you're operating it more quickly, then it replenishes the energy in here and the voltage will be higher. So that's the basic circuit topology that's here. The switch is between Vin and the SW output, the switched output. So just imagine this switch being here, and here's the inductor, and also coming from that point is the cathode of a Schottky diode, which is going to ground. That diode is this diode, and here's the same inductor. Now there's this load or a current sensing resistor, 0.1 ohms, and that's coming off the what would be the right hand side of the inductor here, and it returns to an output filter capacitor and onto the load. So if you just disregard this resistor and you consider these two capacitors to be one capacitor, then that's essentially what we have here. The inductor and a capacitor, the inductor and a capacitor. This is the 1 or 10,000 microfarad electrolytic capacitor. And on this, it's a solid electrolyte capacitor. It's much better for these switching supply applications. And it won't dry out, and its ESR is very low. Then there's this 0.1, which is better for filtering out any high frequency component that's up here. The sensing is done here. The voltage is sensed by this, and it's also sensing between this and the battery terminal. It's sensing the voltage drop across this 0.1 ohm resistor, which is how it can detect how much current is going into the battery that's being charged. And it can adjust what the switch is doing here to get the appropriate voltage and or current going out to the battery. So that's what's going on there. There's also this additional capacitor and another Schottky diode, which have to do with the boost functionality on here. You can think about it as a boot strap, and it's basically facilitating the saturation of the switching transistor. So there's actually a transistor from VN to switched, kind of like this, VN to switched. And you want it to be saturated. You don't want it to be running in its linear region. And the way it's connected here helps with that. That's why that's there, and this diode is associated with that. And I should mention that even though I said that with the inductor in here, you can actually get a little higher voltage, it's not being used in that way. And this battery charger circuit here is a buck controller, or a buck converter. So it's lowering the output voltage to what the input voltage is. So it's taking the input voltage and lowering it instead of raising it up. So I didn't want to misrepresent how the inductor was working there. I was just describing what inductors and switch circuits typically do, but a lot depends on other factors in the circuit. Alright, so now we come to this point where we expect to have a battery out here. And what we actually have out here is the battery voltage booster for when we're discharging the battery, but also through this connection we have this manifold, if you will, where all three battery circuits exist. And again, that's just like what we had here. The output of the battery charger goes to the three cells in parallel, as well as to the input of the voltage regulator boost converter. So it's just like what we have here. So let's say we're in charge mode. The charge controller is running because it's enabled. So it's producing charging current at the appropriate voltage. And it's going down to this point. And there are places to have resistors. R26, R27, R28. Those are just 0 ohm resistors. Those are useful for troubleshooting and things like that. You can remove them, but normally they just have 0 ohm resistors installed, so it's like they're a jumper. So let's look at one battery's worth, but the same thing is true for the others. We supply power to the charge controller IC through this resistor. It's fairly low, 330 ohms. That goes into its VDD, and its VSS is connected to ground one way or another. It could go to ground through this R14, which could be another 0 ohm jumper, but it's left open. We don't want this to be pulled hard to ground right at this point. We want to use these two MOSFETs to get down to ground. And those MOSFETs are under control of the discharge control output, D sub O, or the charge control output, C sub O. And the battery itself is connected between the raw charging input and the connection to ground that's either through the jumper or through the MOSFETs. So the batteries are very much like what's shown here if you strip away the surrounding stuff. The IC here is able to monitor, well, I'm going to go back to the one I was showing. The IC here is able to monitor the voltage across the battery through this low value resistor, which is also stabilized with the capacitor. And some portion of the current is also returned to ground through this VM pin, and that has something to do with it being able to detect the charging current behavior of the battery. These two MOSFETs are actually part of an IC, and you'll notice one of them has a polarity in this direction, the other one has a polarity in this direction, but each of them has an internal diode going the other way. So you can have current going through this diode and then through this MOSFET to ground if this one's turned on, or you can have current going in the other direction through these, again depending on what the protection circuit is doing. Normally I think these would both be just turned on, and then one or the other of them or both can be turned off if the IC wants to disconnect the battery from ground and thereby remove it from being charged or discharged. But if it notices that it's only having a problem in the charge direction, it can leave it connected to ground for discharging but not for charging, and vice versa. So again, 3 times that. The only difference is that at some point somebody decided to make this one 330 ohms, and these two are 390 ohms. My understanding is that was a refinement to the circuit to make it work a little better in some way, but I haven't been able to suss that out. By the way, you don't need to use all three cells. This charging circuit will work just fine with just one cell installed. You don't even need to populate the other parts around these ICs. You could just leave all this blank on the board and just have one cell. Or you can double its capacity and populate it for 2, or you can get the most and populate it for 3. The rest of the circuit will work just fine regardless of how many batteries you have in parallel here. Okay, let's look at the final part of the circuit, the battery voltage booster or boost converter. It's also the voltage regulator. So even as the battery voltage depletes, it holds its output voltage that's going back to the scope at a more or less constant level. Here's the topology that's being used. You have a DC current source out here. It's the DC into this boost circuit. There will be a sense resistor, a low value, and then an inductor, and then a switching element back to ground, and then a diode, and then a capacitor back to ground, and then whatever load we have is across that capacitor. So when the switch is closed here, this diode becomes reverse biased, so it doesn't conduct, and the load isn't connected here at all, but you have current going this way through the inductor and back to ground. Then the switch opens. Again, the switch being a switching power supply type topology, it's rapidly opening and closing. When the switch opens, the inductor has the tendency to keep current going while its field collapses, so it keeps pushing current in this direction, and now the diode is forward biased, and the voltage across this inductor when the switch opens is higher than the DC input was, and so that higher voltage is run through the diode and charges the capacitor up. Then the switch closes, recharges the inductor, but now this diode is reverse biased, so this switch being closed does not discharge the capacitor. It can't because the diode's in the way. So the voltage here can now power the load, and then the same thing happens over and over and over again. And by controlling how often and for how long the switch is open and closed, you can regulate the voltage. So you have to monitor the voltage at some point and then use that to control how the switch operates. So let's look at the equivalent circuit here, or the actual circuit really. It's tied into the output of the battery, the discharge of the battery, and it should be somewhere in the 3.6 to 3.7 volt range. And there's a decoupling capacitor here. Here's the IC, and it has a V in, and it has a sense line, and that's V in and sense. So it's measuring the voltage across this low value 0.02 ohms, and from that it's able to figure out the charging current, or the discharging current really. And then you've got your inductor, and it goes to ground through a switch. In this case, the switch is a MOSFET, and the MOSFET is being controlled by the IC. So again, that's just like this. Then we have the Schottky diode. That's just like this. Then we have the capacitor. It's made out of two capacitors. I inaccurately showed 1000 microfarads is 10,000 microfarads, and then a 0.1 microfarad across it. So it's very similar to what was over here. That is acting as this capacitor. And then we have a load, and that's this voltage divider here, 910K over 100K. So it's taking roughly 1/10 of the voltage here and putting it into the voltage feedback pin of the IC. And from this, the IC knows how to operate the MOSFET here, the MOSFET switch, so that you get the desired voltage out here, which should be about 8 volts. It's trying for 8 volts and maintaining it there. That's when you're in battery discharge mode. This diode also serves to prevent current trying to go the other direction when the scope is providing the power, because it's AC powered at the moment and it's providing power to the battery pack. You don't want that going backwards into this circuit. So besides the functionality of this diode for the switching regulator, it's also a backflow preventer. No, I was full of it. These actually are 1000 microfarad capacitors here and here, not 10,000. I made that correction on my schematic, and I've also renamed this LED scope is AC powered, and it would help if I actually wrote the is on there. Scope is AC powered. Okay, some final nuances. There's this resistor tied from here to here, and that influences the plus input to this comparator and the minus input to this comparator because they're connected together here with this jumper. To understand these hysteresis resistors, you have to first remember that the comparator will work on the tiniest voltage difference between its two inputs and use that to switch the output. If the voltage being measured happens to be really close to the reference voltage and maybe just moving a tiny amount around that, it's possible for the output to chatter, to rapidly switch on and off. It's kind of indecisive. And it'll react again to the tiniest amounts of noise on the signal or whatever. So it's not desirable to have that. So you want to force it to require a bigger disparity between the two input voltages before it will switch as output. And that's called hysteresis. On this type of op-amp based comparator, if you do the math from the voltages here and these two resistors and add the influence of this resistor, keep in mind that if this output is low, it's pulling this point to ground. So it's essentially like this is ground. That puts this resistor in parallel with this resistor, changing the overall value down here, the bottom half of the voltage divider. But if this is not trying to pull low, if it wants to be high, remember these are open collector, they can't actually drive high, but there is a pull-up resistor to VCC that will pull it up. So when it's in that mode, then this resistor, the hysteresis resistor, is essentially in parallel with this resistor, thereby changing its effective value. So depending on whether this is high or low, this voltage at the middle of the voltage divider is moved up or down a little bit, and thereby changing how this comparator switches, well actually both comparators, but this is the primary one, in relation to its 0.4 volt internal reference. I did the math, and essentially what's happening there is it's changing that center node by about 0.03 volts. up or down from what it would be without this resistor. So that's the amount of hysteresis there is. It may sound like a small amount, but it's adequate to keep the comparator from chattering. I think I already mentioned that these jumpers here, here, and here are there to defeat the protection circuit, since ultimately the only thing the protection IC can do is disconnect the minus side of the battery from ground if it detects something is wrong. So if you don't want to have that protection for the sake of troubleshooting, you can just put a jumper on here temporarily to just take this directly to ground. Then this IC is just along for the ride, but it can't influence anything. And as part of my own troubleshooting, I had these shorted out, and it didn't change the way anything was working. So I was able to be reasonably sure that that wasn't where the problem was that it was having. Looking momentarily at the original circuit, which is full of my notes, the NTC, negative temperature coefficient, I think is what that stands for. It would go through an R25, which is shown as 0 ohms here, and then R21, R22, and R24 in parallel, and those are shown as variable, and back to ground. These would be the thermistors, and there'd be one installed for each battery that's in there. If you've only got one battery, you'd only need one thermistor. And then you can either just use this as a jumper to connect or not connect those, or you can add it to add some overall resistance to what these are doing, as may be needed. But those were just put on as sort of an afterthought by the circuit developer, according to the email he sent me. And he didn't really ever implement it. It should be possible, but essentially you would leave these thermistors out. They're not on the DigiKey bill of material, and you would leave out this resistor as well. Although if these are gone, then having that resistor or not having it wouldn't change anything. You could have it there or not. But in my version of the circuit, I just show the NTC pin as being not connected. I found this Molex part. This is their part number 00260-33031. It's a 3-position connector with the distance between centers, or pin centers, of 3.96 millimeters, essentially 4 millimeters. Date code 1934. Doesn't seem quite right. Wonder what that's all about. Anyway, this is what it looks like. It's offset on one side, so the pins are not centered from left to right in this view. But it just, you can crimp or solder on those little connectors. Here's one. And then snap them in there with the wires hanging out the back side. Here's the Molex part for that, 00085000106, and it's good for between 24 and 18 AWG wiring, which is certainly in the range of what would be needed for this scope battery. I found that this was a little bit tight in this direction from finger to finger to fit into the space available on the scope. So I just put it on some sandpaper and sanded off this face and the opposing face. It's already fairly thin. I didn't have to take off very much though, and I focused more on taking off plastic at this end, the end where the pins go in, as opposed to the back end. It has to fit in between these walls here, and of course you have to put it in with the holes down, but it just goes in there perfectly that way. So I think that'll be a good solution for that. And this is the Sullins connector solutions. It's a pretty generic part, but this is what's called for in the DigiKey bill of material. It's a 3-pin 0.1-inch centers female header with PC board pins on it. This will be the connector that goes onto the short cable that ends up plugging into the oscilloscope's battery terminal or connector. Alright, I have the 2 red leads and the black lead. These are stranded wire 22 gauge with some shrink tubing over them, sweat soldered onto the PC board pins of the 3-pin header. And then I don't have the proper Molex crimping tool, so I just use my needle nose pliers to bend over the tabs and then solder them in place, and then bend over the strain reliefs over the insulation. That works fine. Now I just have to insert them into the already prepared, by that I mean sanded, connector body. Alright, there's the finished battery cable with the 2 red leads on the outside and the black lead in the middle. Okay, there it is. And there's enough wire to go around and plug into the battery pack. I think these are on there good enough. It feels like there's some resistance. Well, that's a big disappointment. This won't actually work. You can kind of see where the folded over part of the connector is. That's where the pin has to go into in order to make contact. Otherwise it's just into that sloping area. The pins on the Tektronix scope are only 1/4 inch long, and if I put those in as far as they can go, they're only barely making it up to the point. It'll be a real tenuous connection, just barely touching the tip. That is not reliable for power. I have to come up with a different connector. Son of a gun. And this is the Adafruit cable. They call it the jumper wire, female to female. They're 6-inch long wires. They're 28 AWG, so a little bit on the small side. But as I already demonstrated in my experiment, they should still be adequate for the currents involved. That's the Adafruit number 1950, and there's DigiKey's part number if you buy it from DigiKey. And it comes with these ribbon cables, but because they're jumper wires, I think you're really intended to peel them apart into individual conductors, each with the female connector at each end. You can, I suppose you could still use them bundled like that, but I think that that's just convenient because that's the way the ribbon cable comes. And you just peel them apart. Trying to make a new cable from the scope's battery connector up to the battery pack's connector. I'm checking out these Adafruit clips. They're just breadboarding clips, but they're female on the end instead of male on the end. They will fit the pins on the scope, which are the same sizes as these, albeit on a 5/32 inch spacing instead of a 0.1 inch spacing. The scope draws a maximum of 700 milliamps from the battery when it's in the mode where the scope is not getting AC power and is getting it all from the battery. So a maximum of 700 milliamps. If it actually tries to draw more than that, the scope will shut itself off. I've already tested this one conductor from this Adafruit cable at 700 milliamps, and now I boosted it up to 1 amp, which is the highest expected charging current from the scope to the battery pack. I've got my power supply set to 9 volts and a 1.5 amp limit. I've got it running down through a pin header and then running through that little Adafruit wire, and then continuing on through a succession of cables up to my DC electronic load, where we can see that it's pulling 0.998 amps for a programmed 1 amp. It's measuring 8.45 volts up here, so 0.55 volts are being dropped in all this wiring. But the cable isn't even, maybe you could imagine the slightest warmth on it, but it's definitely almost room temperature. So at the maximum expected current, it's not a big issue. That 0.55 volts is being dropped over all the wiring going out to the load and back. So this is a 24 gauge wire, and that should be rated for about 1 amp. Also, I'm checking the conductors just with the old finger test, and I don't detect any warmth from them, so they seem to be making decent contact. I just did a voltage measurement across the two ends of this Adafruit wire, and it's 0.07 volts drop. So the rest of the 0.55 volts that's being dropped is being dropped in the rest of the wires, as expected. So a pretty negligible voltage drop. It won't affect anything. So I think these are actually a pretty good choice. The thing that it doesn't assure is that apart from using red and black Adafruit wires, there's nothing to tell somebody which one goes on which of the 3 pins on the scope. You'd have to color code them with a dot of paint or a label or something. Anyway, I think that's a viable way of doing it, but there may be better ways. I have this Samtec. It's for square pins. It's for exactly the type of pin that you see on these headers or on the connector on the scope. So it's a gold-plated connector at the place where it would go over the pin, and then it has the usual place where you can crimp or solder the bare end of a wire into it, and then crimp the 2 tails over as a strain relief. But those are made by Samtec, and Samtec does not sell any corresponding connector housing with a 5/32 inch center spacing, which would be required for this. They suggested that maybe it would be not too difficult to 3D print up a housing, and I may do that. This is using the Adafruit female pin headers Individually plugged over the 3 pins there. Although if I didn't care about the colors, I could have just used 3 adjacent wires because it's sort of a ribbon cable. But I peeled out 2 reds and a black, so that's why they're not connected together. But those fit over there as well, and this is the wire that I tested for current to make sure it wasn't dropping too much voltage or getting warm or something like that. This is the smallest gauge of the 3 options that I came up with. So workable, but my third choice for sure. Here's the Amazon listing for this other alternative set. They call it 15 sets, 60 pieces, JST, whatever that stands for, VH, 3.96 millimeter pitch, which is the same thing as 5/32 inch. So 3 pins, 22 AWG silicone cable. It comes with the male connector to go into a circuit board, and again you would solder this into one circuit board and then the wires into the other place on a different circuit board, and then plug that into that to connect the 2 boards. And that's particularly useful if you have maybe 2 circuit boards that plug into each other normally, but you want to work on the assembly, so you want to be able to separate them a little bit. I think that's why they call it an extension cord. They don't really say what it's used for, and they do have it in 2-pin, 3-pin, and 4-pin versions in a bunch of different styles. So that style of connector, that style, this style, that one, a whole bunch of different styles of connectors. That is the one that I used. Or is it this one? Oh, the difference is that with the JST VH, the one connector that goes on the board has straight pins. If we get the SMT one, then it's the same thing, but it has right angle pins. Otherwise the same animal. And it even comes with shrink tubing, although I don't know exactly where you'd use that. Anyway, so that's where to buy those on Amazon. I think the wire gauge is 22 gauge, and it's silicone rubber insulation, so pretty nice. There is a clip on the connector so that it would snap onto the other one, and you'd have to push a bendy piece of plastic to get it to release. I've cut that off with a razor, or an X-Acto blade. And with the side with the holes facing down, it fits on there very nicely. That would be a good solution to this problem. It feels like it has a nice grip on them, but it comes off all right. So that's another strong possibility. And there's my second best, maybe the best if people don't want to screw around with 3D printing a housing. This is the one I bought from Amazon, which I'll show the description so people can look at it. And I have taken a razor blade to it and cut off all the protuberances on here that would get in the way of it fitting into the confines of the scope connector area. but it's not a very hard plastic, so that comes apart pretty easily. I also use my diagonal cutters to chew away the majority of it, and then the razor blade just used, or the X-Acto knife, just to do the final trimming. And I've soldered on a similar female pin header, or yeah, female pin header, very similar to the one used from the bill of material for the battery pack. Alright. There, that fits just fine as well. Similar wire gauge. I forget exactly what this is specified to be, but it's big enough for the application. And then if we look at the battery pack circuit board, this goes in like that. And there are the Samtec connectors, or contacts rather, that should fit into this 3D printed housing. So it's a gold-plated connector at the place where it would go over the pin, and then it has the usual place where you can crimp or solder the bare end of a wire into it, and then crimp the two tails over as a strain relief. Alright, there's the design for the connector housing. It's in two parts, a base and a lid, which will have to be glued on to the base. I decided that it would be difficult to get all the precision nuances in here, having it printed as one part. So I can only get in within 1/10 of a millimeter tolerance on this, and that's at the design stage. I'm not sure if my printer can actually print anything near 1/10 of a millimeter in accuracy. I've never asked it to do more than just 1 millimeter resolution, although it seems to do that pretty well. So we will see. This whole thing's success hinges on the printer's ability to actually print this thing. Now the colors are just there to help me keep things straight, but so you've got a base plate that's in gray. You have 4 dividers that'll be the wide part of the connectors that go into here, where they crimp on and get soldered onto the wire that will come out here, here, and here. And then the sort of teal, or whatever that is, are the barriers for the part of the connector that, or the contacts that actually makes contact with the pins that'll come in through the face plate, which is perforated by these slots. That's the green part. And then each of the contacts has a finger on it, a spring-loaded finger that'll allow it to go in this direction, and the finger snaps down into these dark gray things are actually negative space. That'll be a slot when it's printed, so it'll spring down into there and prevent it from getting pushed backwards when you drive the pins in that way into the connector. Again, the tolerances on this are very tight, and the part is tiny, and I'm not sure if it'll actually work. But the only way to tell is to try it. Now, with the inherent dimensions here, some things are very particular that they need to be in inch increments and at high precision, but other things seem to be better in metric, so I'm building it all in metric and rounding to the resolution of the software. That's, again, 0.1 millimeter, and fudging things a little bit here and there, and it'll be interesting. And there's the extremely simple design for the top plate or cover of the connector housing. It's just a block with a negative space block of thin dimension or thin thickness laying on top of it. And there those two parts are after dragging them into the Prusa slicer application. There's one of the contacts fit in to its slot in the housing. Somehow I ended up miscalculating how long the housing should be. It needs to be a good millimeter longer in that direction. Let me see if the lock on here works. See if that little tab that's down in there is fitting in the slot properly. Alright, I've got the Samtec contacts soldered and crimped. They're not crimped the way that they should be done with a special tool. I just use a needle nose pliers to bend the crimp tabs over the stripped wire and then solder that spot, and then likewise use the needle nose pliers to bend over the strain relief tabs and kind of squeeze them around the insulation. I usually do that with Molex connectors when I only have a few to do. Wouldn't be any good for production line quantities, that's for sure. So now I have to fit this into the housing and see if it all goes together as expected. Alright, there's the housing around the three contacts, and I've used tiny dots of super glue administered with the tip of my X-Acto knife, and then squeeze it together and make sure it's in alignment, give it a blast of accelerant, and hopefully it'll go on to the connector on the scope. I did have a little trouble with the one contact here on the left. I gave it just enough leeway in the housing so if there wasn't a precise alignment with the pins that it could wiggle just, you know, a tiny fraction of a millimeter. And this particular one wants to sit a little bit off to the side. I think that's more of a printing error. The actual dimensions in the 3D design software were within 1/10 of a millimeter, and that's as close as it could get. So hopefully this will still plug in. Alright, let's see how it goes in. Pretty as you please. Fits in between the plastic walls on the scope perfectly. No wiggle room, but it also isn't tight. It fit over the connectors just fine. And I know that those Samtec connection points have bifurcated contacts, so it's not only making contact with the housing, but it has those two bifurcated spring contact points which then push against the pin that's stuck into it from two different sides. It has a good snug feel, but yet it comes out alright. So I'm going to plug this into a pin header now and make sure I have good electrical continuity. I think I'm actually going to leave the housing design the way it is. There's no way these are going to short together, and having them slightly exposed like that allows probing with the point of a test lead into those so you could monitor, you know, voltage and what have you, because there's that little bit exposed. And there's the one with the 3D printed housing and the Samtec contacts. In this case I was able to use the red wire for both of the positive leads, but in this case because it already comes with the green wire, I couldn't do that. But it doesn't matter. If you plug it either way around, it'll still work. So the color is not important. Alright, this is the alternate battery pack, the simple nickel metal hydride approach without all the circuit board complexity. It'll probably work at least as well, although it certainly won't have as much milliampere hour capacity as the other approach, the more complex approach. These just don't pack the amount of charge in them as the lithium ion cells do, but this is much simpler, not necessarily cheaper. These just regular Energizer nickel metal hydride AA's are about $17 for just 4 of them, and I need to have 14 of them to get up to approximately the right voltage. It's interesting how they practically hide the technology on here. Energizer Recharge Power Plus AA4, I guess that means 4 AAs. Longest lasting rechargeable battery. World's first. Made with 22% recycled materials. Pre-charged. Finally gets down to 1.2 volt, 23 milliampere hour nickel metal hydride. That's the only important thing about what's on there. Now I was going to use a total of about 8 cells in series and then make a parallel bank to get more capacity, and I actually have enough cells here to do that. The thing is, I watched a couple videos of other people who did similar things, and they were getting good voltages just using 14 of them, using 14 of them instead of 16. So I'm going to do likewise. Well, these are pre-charged, they're supposed to be fully charged. I'm going to connect up 7 of these in series and see what the actual voltage is that I can expect from them. So I'm soldering these up in pairs, and it's important to get them aligned. So I just made this little tool here, just a piece of, what is that, 1/2 inch, 3/4 inch plywood, whatever, and I cut an accurate right angle out of it, and that allows me to put one cell up in the crotch of the thing and then put a bead of super glue along one edge. Doesn't have to be super glue, it could be epoxy or something, although super glue will be a lot faster, and then just get the other one aligned with that and it'll be straight and level. Not strictly necessary, but I give it a very brief puff of accelerant just to make sure that it's fully cured when I take it away from the jig. And then I just use a little piece of paper towel to wipe off the residue of the accelerator. It should evaporate anyhow, but meanwhile I've been topping off the battery on my micro spot welder. Looks like it's fully charged now. I cut out 6 pieces of thick cardboard. This is the kind of stuff from the back of a tablet. Some of the cheap tablets have really thin cardboard that hardly offers any kind of a clipboard-like support for writing, but some of them have a greater thickness, and that's what I used. I just carved up 6 little pieces there, 28 millimeters by 48 millimeters, which should be about exactly the size of the battery housings, not including the buttons on the ends. Yeah, you can see that the cardboard is that big, and it lines up with the edges if you take parallax into account. And there are 6 of them because there's 7 pairs of cells. For the next step, I just use the fence of my table saw and put this piece of wood on it so that it's 90 degrees. And I'm going to use that as a way to assure that these are getting lined up properly. I made a little mistake there because I left the tape on that side, and I shouldn't have, not so far as where the batteries are going to go. I need to peel that back a little bit because right now it has a bit of a radius there, and that'll make the left side of the cells sit up. So I can get one up there, and its piece of cardboard, if it doesn't fall over. Right now it wants to go under the battery, and then I can put the next one up that way, and so on, and just glue them all up in the same way I glued the 2 cells together. Now I actually thought I was going to use Mylar because I have big rolls of Mylar from a job I had almost 40 years ago, and we used it for drafting and insulation and all sorts of things, even as shims, and I use it for a lot of projects, but I found that it doesn't super glue worth a damn. Every time I've tried to secure it with super glue, the super glue hardens and it just doesn't seem to stick to it. Not quite sure why. Maybe super glue requires a tiny amount of porosity, and maybe the Mylar doesn't have any. Maybe it just can't get a good grip. I'm not sure. Anyway, so I'm using cardboard here. That should be easier to deal with. Alright, 1, 2, 3, 4, 5, 6, 7 times 2 plus 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 plus. And a pretty solid feeling brick. So I don't need this jury-rigged lash up for alignment anymore. That's moisture from the accelerant that I used. Alright, I put a couple nickel-plated steel strips, 0.15 millimeter thickness. I cut it down to, I don't know, about 5 millimeters wide from the 8 millimeter tape I had on hand, and I did 4 spots per cell. Now I'm going to put one across the middle, and there's the other side. So to avoid soldering directly to the batteries, I'm using, or I did use, the micro wells with the strap, and then when I could solder to the strap I used that. I tried it in one place using a strap across, which was quicker, but it had a good chance of blowing holes through the first strap. There was no extra metal behind it to act as a heat sink, I think, so it was very aggressive on the thin strap material. So I decided to revert to soldering the straps only to the battery ends where the welding works very well, and then using the soldered wire. I only had 22 gauge bus bars, so I made a long rectangle and soldered the ends, so that's, even 122 gauge would have been fine, but I doubled up. I measured 8.96 from one end to the other, which is about right. 8.96 divided by 7 is 1.28. These are rated between 1.2 and 1.3 volts, so that's about right. That's for a fully charged cell. And that's the desired voltage for the scope. So I think 1, 2, 3, 4, 5, 6, 7 paralleled cells is the correct number. I took another piece of cardboard and just taped it over. So this is the minus side of the battery stack, or stack of cells rather, and the minus wire from, this is one of the ones from Amazon. I've already trimmed the extra plastic bits off of there with diagonal cutters and a utility razor blade, but I'm going to run the black lead across the top of this and solder it to here. Alright, I have the black wire connected there. The outer two wires from the connector, they should both be red, but it's red and green here, going into one side of a little fuse circuit board that I made a whole bunch up of to have a lower profile panel mount fuse holder for 3AG size fuses, and I have a 1 amp fuse in there, so the same rating as the fuse on this thing should be enough. And then the other side of that goes to the plus side of the battery pack. So now I just have to stick a couple of pins in here and make sure I still have the voltage coming out here. Alright, there's the completed battery pack. Nickel metal hydride. I've got it all taped up with electrical tape going both directions, around this way and around that way. I have my fuse holder just taped on one end, and there should be enough wire coming off of that to reach the plug on the scope. I'm not even sure I have to pad that. With the fuse on the end, it pretty much takes up the whole available space in there. And there's the scope running on that power. It is not plugged into AC. And now I'm powering the scope off of AC, so presumably the batteries are charging, or the scope is putting out whatever voltage it puts out to charge them. I think it's a little bit over 9 volts, 9.9 volts if I recall correctly. So it's a little bit higher than this puts out when it's fully charged. So it should bring it up to at least that voltage or close to it. So that's successful. And really, although again the current or ability to put out power on this, it's 2500 milliampere hours times 2, so 5000 milliampere hours, whereas the lithium ion one, those are 2500 milliampere hours also, and there's 3 of them, so and that gets dropped a little bit when you have to step the voltage up, so it's maybe even comparable to this, and it's a lot less complex. This is a very interesting circuit, and one of these days when I feel like messing with those tiny parts again, I'll finish debugging it, figure out what it is that's causing it to cut out. I might have a dodgy solder joint on there, but I'll still go through and talk about the circuit theory on that since I've invested a certain amount of time on it. But anyway, this is, I think, the winner. Ultimately less expensive, simpler, and yeah.